In this video, we will discuss several practical aspects of neural network training such as initialization, preprocessing, mini-batching, and tuning. Even though these aspects may seem like an afterthought, they are very important both to the convergence behavior of the training as well as the properties of the final trained model. This video will discuss several of these practical aspects of training. In the previous lecture, we discussed the backpropagation algorithm. During the execution of the backpropagation algorithm, it is useful to know whether an error has been made in the implementation. Fortunately, this is easy to do using numerical methods. Let LW be the current value of the loss. The first step is that the weight of this edge of a randomly sampled edge is perturbed by adding a small amount epsilon to it. Then the estimate of the derivative of the loss function with respect to this edge is given by LW plus epsilon minus LW divided by epsilon. This follows directly from the definition of a derivative. So we have an estimate of the partial derivative using this type of numerical method, and we have already calculated the derivative of the loss function using backpropagation. When these two partial derivatives do not match closely enough, it might be indicative of an incorrectness in the implementation. So, in the previous slide I mentioned that the two have to match closely enough. So what does closely enough really mean? Because we have no real reference point in terms of knowing what the absolute values of the partial derivative should be. This can be achieved by using relative values. So let GE be the algorithm determined derivative. This is the derivative computed by the backpropagation algorithm, and let the approximate derivative be denoted by GA. Then we compute the ratio shown in equation 13. If this ratio is less than 10 to the power minus 6, that's a rule of thumb, then you can assume that the algorithm is working correctly. Now one point is that often the errors tend to be high when the ReLU activation function is used. In the case of the ReLU, the ratio should be less than 10 to the power minus 3. The reason for this difference in behavior of the ReLU is that the ReLU has a specific point at which the gradient suddenly changes. Now this type of check should be performed for a sample of the weights and at a few points during the training. Next, we discuss the issue of stochastic gradient descent and mini-batch stochastic gradient descent. You would have noted that all our loss functions so far are defined in a point-wise fashion. So what this means is that the loss function is defined for a specific point I. Now this really, the resulting updates are really considered stochastic gradient descent. This is because the true loss function is additive over the points. So for example, when you're performing regression, the true loss function is simply the sum of squared errors in the regression. And when we just take the loss over a single point, we are only using a randomized approximation of the true loss function. And the computing this gradient over a single point is like a sampled gradient estimate. So all this while, all the gradient updates that you have seen, they are stochastic gradient descent updates. Now the main problem in stochastic gradient descent updates is that sometimes it may happen that using single points may not give you an accurate enough estimate of the derivative of the loss function. Now one can improve the accuracy of gradient computation by generalizing this idea of sampling points. So in the case of stochastic gradient descent, we are sampling a single point. We can generalize this to sample a batch of instances. So the idea is that when you perform the forward propagation, you will perform the forward propagation over a batch of instances, and similarly then you will perform a backward propagation over the whole batch of instances. So instead of holding a vector of activations, you will hold a matrix of activations in each layer during the forward phase, and during the backward phase you will hold a matrix of gradients. So typically you will need matrix to matrix multiplication both during forward and backward propagation. This increases the memory requirements, but in general you do not need large mini batch sizes. So the typical sizes that you need are powers of 2, such as 32, 64, 128 and 256. The reason that you choose typical powers of 2 is because that is the most efficient way in order to implement these operations. Now, why does mini-batch matching work? One reason is that at the early learning stages, the weight vectors are very poor and the training data is highly redundant in terms of the important patterns. So even if you use very small batch sizes, it typically gives you the correct direction of the gradient. However, at later learning stages, the gradient direction becomes less accurate. But when you are using mini-batch stochastic gradient descent, you are adding some amount of noise to the learning process. But as you will see in later lectures, adding some amount of noise helps avoid overfitting anyway. So the performance on out-of-sample data typically does not deteriorate, even though the gradients that you have computed are somewhat less accurate. The other issue is that of feature normalization. So, in feature normalization, there are two types of feature normalization that are used. One is standardization. In standardization, you normalize each feature to zero mean and unit variance. The second is whitening, where you use the correlations among different attributes. So, in whitening, what you do is that you transform the data to a decorrelated access system with principal component analysis. Principal component analysis is essentially a mean-centered version of SVD, which you have seen in previous lectures. Then, just as in SVD, you truncate some of the lower order components. Here also you truncate the directions with extremely low variance. At the very least, you want to truncate the directions in which the eigenvalues are extremely low. That means the variances are extremely low. Typically, they might be even low as 10 to the power minus 6. In many cases, the variances are really zero, and these very small variances are being caused by computational errors, or they are dominated by computational errors. So you drop these directions, keep the other direction, you standardize them. So you scale those other directions to make them unit variance. Now the basic principle here is that the data, you are assuming that the data is generated from a Gaussian distribution, and in the absence of any knowledge about how these independent directions are related to the loss function, you give equal importance to all directions. And then you simply let your neural network learning algorithm learn the weights and decide which directions are important. The second issue is weight initialization. Initializations are surprisingly important. Poor initializations can lead to bad convergence behavior. In fact, one of the key aspects in neural network training is that is the recent research in picking good initializations, because it has been found that when you are working with very deep networks, then you have an instabilities in the values of the gradients across different layers. This leads to a problem called the vanishing or the exploding gradient problem. And there are more sophisticated initializations to deal with this issue. And these sophisticated initialization techniques like pre-training, they are covered in a later lecture. However, even if you don't use these sophisticated pre-training methods, even some simple rules for initialization can help in conditioning. So the first important rule is symmetry breaking. It's a bad idea to initialize weights to the same value. So what happens is that if you initialize all weights to the same value, it results in the weights being updated in lockstep, and it creates redundant features. So the average, so it's important to initialize the weights to random values in order to break symmetry. However, what is the magnitude of these random variables? The average magnitude of these random variables is also important for the stability. So one issue is that the output of a neural network is sensitive to the number of inputs. There's an additive effect of multiple inputs, and you can show that the output, the variance of the output, linearly increases with the number of inputs r, which basically means that the standard deviation scales with the square root of the number of inputs r. So in order to normalize for this fact, what we typically do is that you initialize each weight from a Gaussian distribution with standard deviation square root of 1 by r. In the case of the ReLU, there are some results that you want to use square root of 2 over r. And now, you can even initialize from a uniform distribution within minus 1 by square root of r and plus 1 by square root of r. Generally, the performance is very similar whether you use a Gaussian distribution or whether you use a uniform distribution. The other point is that the stability of the performance of the training also depends not just on the number of inputs but also on the number of outputs. So a more sophisticated rule is to use 2 divided by the in degree of a node plus the out degree of a node. This initialization is referred to as Xavier initialization. A neural network will have a large number of hyperparameters. So these hyperparameters can represent, for example, the number of layers, the number of nodes per layer, the learning rate, and the regularization parameter. So in each case, it's very important to use a separate validation set for training. You never want to use the same data for backpropagation training as for tuning. As you'll see later, doing so leads to suboptimal values of the parameter because you are essentially overfitting. So how do we choose the parameter values to test? Typically use a technique called grid search. So for each parameter, you select a set of values in some reasonable range. And then once you have a set of values for each parameter, you can determine all the combinations of values. And you can test over each combination of values and pick the best combination. This technique is referred to as grid search. Now, one point that you have to be very careful about is that sometimes grid search will give you an optimal parameter which is at the border of a of the range of values on which you are searching. In that case, you have to extend the range of values because you don't know whether you have found the optimal value of that parameter or not. One optimization that you can do is that sometimes the number of possible combinations can be very large. So what you can do is that initially you can search over a coarse grid. So for example, for each parameter you may test only 3 values. And then once you have found a range of values in which these parameters work well, then you can drill down into that region over finer grids. Now, one question arises is that how do we pick the set of values for each parameter? So one possibility, of course, is to use uniformly distributed values of the parameters. Now, this is not the best approach in many cases. The better approach in many cases is to use log uniform intervals. So here what you do is that you search uniformly in reasonable values of the log values and then you exponentiate. So for example, let's say you decide that for your learning rate, the reasonable value is somewhere between 10 to the power minus 1 and 10 to the power minus 3. What you do is that you uniformly sample the log learning rate between minus 3 and minus 1 and then whatever value you sample, you raise it to the power of 10. Now, this grid-based approach can turn out to be very expensive, especially when the number of parameters is large. So for example, let's say you have 10 parameters and you choose just 3 values for each parameter. The number of possible combinations is 3 to the power of 10, which is around 60,000 possibilities, which means that you will have to train the neural network 60,000 times. This is not very efficient, and in some cases, in many cases, it might turn out to be impractical. A more flexible choice, rather than picking specific grid values, is to sample over the grid space. So you have a reasonable range over of the parameters, and then you sample over the grid space. For some parameters, you use the log values of the parameter for sampling, but in each case you are simply sampling over the grid space, and in fact this is used more commonly in large scale settings. Sampling over the grid space has largely replaced grid search. So when you have large scale settings and assuming that multiple runs can fit over a single platform, one trick that is used is that you typically run multiple threads with sampled parameter settings. And the accuracy is tracked on a separate out-of-sample validation set. Bad runs are detected and killed after a certain number of epochs. And then new runs may be started after killing the threads if needed. In most cases, what you do is that a few winners are trained to completion and the predictions are typically combined in an ensemble. This type of approach can be useful in at least some settings.